where we've got to in terms of the perceived energy gap going forward to the end of the century, we're going to ask ourselves what are the implications of that energy gap. We're going to remind ourselves a little bit about efficiency, in particular Carnot efficiency, and what the implications of that are going to be, again going forward with respect to the energy mix that we're going to have to look at. And we'll make some concluding remarks again. And in the last 5 minutes, I'll go over some hints and tips for revision for the examination paper. Okay. And again, all this will be on Blackboard. So, what we said was that a large fraction, although not all of our energy, is of course used in generating electrical power. If we have to change energy sources in terms of removing fossil fuels, then the simplest substitute has got to be to try and utilize a source that can be used in the same way. That would be more efficient. And that generally means large central facilities. Now let's consider the global sources again. Again, we're going to use Qs, and we're going to look at the global requirements rather than regional or country by country. But let's remove solar power just for the moment. And we said that our S2 total was about 0.5 Q per year. That's only about 10% of our projected 5Q demand by 2080, end of the century. But we've not taken into account the way the energy is actually provided or delivered to the point of use. And of course that means there are various efficiency issues we have to consider. Also remember, we've got these two constraints heading towards that 5Q per year of steady energy use by roughly 2080. First of all, we said and showed that the expiry of oil and gas resources is going to have to be taken into account. We're going to have an increased pressure in terms of greenhouse gas emissions to try and limit global warming. And that means we're going to have to exploit all those alternative resources we talked about to their fullest extent, which is going to be a challenge. However, there is some good news buried in all this. For example, half a Q per year in terms of those alternative resources for electrical power would actually displace about 1.5 Q per year of fossil fuels, because remember, when you burn fossil fuel to generate electricity, you're typically only looking at about a 30% efficiency, so roughly a factor of 3. Some of the really big power plants, large scale ones, can maybe get up to 40%, but let's say 30%. So you can displace 1.5 Q per year simply from alternative energy sources. The bad news, of course, is that that's not enough. We have to replace, remember those pie charts we looked at in terms of the contribution to our electrical energy needs, we have to replace all the fossil fuel. We do have coal, but we'd like to keep that in terms of its use to a minimum because of the climate change impacts. Although there are now programs trying to look at carbon capture to mitigate against the CO2 emissions from those fossil fuel emissions that coal tends to dominate in terms of the amount of CO2 per energy it generates. So if we were to use coal, then we should limit its use to no greater than current levels of fossil fuel use. Total energy consumption, say 0.4 Q. Now, so we reserve Q for special applications only. Let's say we'll only use it at, say, 0.25 Q per year for emergencies, etc. So that leaves us with the alternatives in terms of those other sources of energy we talked about. Solar, fission, and fusion. So that leaves us with 3.25 Q per year to find. Where are we going to get that from? Now in practice, using all of those sources means that most of the energy has got to come from large central facilities. Not everybody can have a solar farm in their back garden. People are looking at smaller scale fission plants, for example in Sweden. But effectively we're looking at these large central facilities. And people often ask, well, what's the maximum we can actually provide from wind and solar to the energy mix? Well, a recent survey in the United States, which is well placed for solar and wind, because of the amount of land they've got, they reckon that they might just provide 50% of the total United States electricity requirements. But that would be a major challenge. You've got to balance all those different energy sources to prevent blackouts. So we still have 45% to find. So, these may not necessarily be electricity producing. Some transformation has to take place to provide an energy source in a transportable form. For example, particularly where we're looking at transportation, it's unlikely that any such system would operate with an efficiency greater than that of an electric power station currently, 30 to 40%. So we have to think very carefully about the efficiencies and how we deliver that power to the point of use. Now, again, there are all sorts of other ideas being floated, such as carbon capture, which is still in its early stages. If you're interested in that, look at Carbon Engineering, which is a company in Canada which has demonstrated a small-scale plant for what they call negative net emissions to replace, for example, fuel used in transport. Other people are suggesting hydrogen fuel, and there are indeed hydrogen transportation systems, for example, in Germany. But again, they're relatively small scale at the moment. So we face the prospect of a significant change in the way energy is going to be delivered for our use. At the moment, the bulk is delivered as fuel, as we said. It's burnt at the point of use. But in future, the bulk may have to come still from central power stations. That's going to require a massive investment program because of the efficiency issues associated with all these alternative energy resources. So it's going to require a change in the total energy demand. And for example, if we compare the present situation in terms of the fuel burnt at point of use for industry or heating, etc., versus transport, at the moment we're looking at, say, an efficiency of 75 to 80% for fuel burnt at point of use. For transport, 25%. If we were to suddenly convert to an all-electric economy, that efficiency goes down to 50%. For transport, well, in this estimate it was 16%, although there are people who argue that it could get back up to 25% at least with modern electric vehicles. But what that means, of course, is as the efficiency goes down, the factor increase in fuel demand is going to go up between 1.5 for transport to 2 for electrical power required for fuel burnt at point of use applications. So, if we were to look at, for example, all electric transport, AEE, stands for all electric economy, if we have a transport, most forms of electricity transport are going to require some sort of onboard storage, batteries. Then we have to think about the storage, the extraction and use, and these all add to the overall efficiency of our electric vehicles. For example, batteries will charge and discharge, maybe at 75% efficiency. Motors, in terms of taking that stored power and converting it to the wheels, will be about 75% efficient, although people argue the more modern electric motors might get up to 90%, but let's keep it at 75%. So 75% times 75% gives us 40%. And of course, we have to think about where the electricity comes from. 40% efficiency is optimistic, so we're back down to 16% in total where that figure comes from in the AEE table there. So efficiency is a very important component of our thinking. So this is an example from a few years ago showing the estimates for the United States economy, and again we've divided the economy into those three sectors we mentioned: household and commercial, transport and industrial, which we said were roughly the same. The units here don't matter very much. What's important is the efficiency. So the total units in terms of direct fuel supply is 47.6, but notice the efficiencies. Household and commercial and industrial are 75%, transport 25%, which we mentioned previously. So if you multiply those by the direct fuel supply, you get the useful work out. Now look at the comparison with an all-electric economy, 40% here instead of 75%. That, of course, is going to increase the primary energy demand that you need. So you go from 47.6 to 84.2. Adding in all the other electrical components for the economy, we're looking at a total increase from 64.6 to 97.2 in terms of the primary energy demand. So the efficiency question is very important. All this, of course, assumes that because of larger electricity generating utilities, these efficiencies are quite close to the maximum. Even so, the primary fuel demand is going to rise by about 50% for the same amount of work that we do now. Another way of putting that is that the waste heat emitted into the environment would double. So where does that leave us? Well, we can change these calculations and the numbers that will change all the time, but we are in no doubt that central power stations might be bad news if we went down this route for attempts to reduce the total energy demand. They're also bad news commercially, some people argue. So what do? Well, solar power is really the only alternative that's large enough to render, for example, nuclear power unnecessary if we get rid of nuclear fuel, of fossil fuels. So again, however, we have to consider the so-called efficiency question in a great deal of detail. And to do that, we have to overcome what's called the Carnot factor assessment. So for all these alternative replacements, we have to think about the efficiencies in the Carnot factor. Remember, the Carnot factor is central to all problems where we have to maximize the efficiency of an energy conversion process that goes through some kind of heat stage. So, just to summarize that part of the course, resource questions are summarized as follows. Fossil fuels will be exhausted quickly, that's oil and gas, or restricted by climate change fears, coal. They might be extended a little bit using unconventional sources, but not by much. We have alternative energy sources, but with the exception of solar power, we're limited to globally about 10% of the planned 5Q per year target. But remember, we can replace 30% of the fossil fuels. Fission, fusion, solar, these must make up the shortfall. The question is which one? No one seems to want nuclear power if we can help it. So we also need to examine the targets that we've set here to see how rigid they really are. Now, of course, some countries have already made the decision, such as Sweden, Belgium, France, Finland, Norway. They've actually gone down the fission route, combined with alternative energy resources. We'll mention that again in a moment. I'm assuming that you're all familiar with the Carnot cycle. If you're not, please go through the next 2 or 3 slides just to remind yourself in terms of what the Carnot cycle is with respect to an ideal heat engine, where we have a source, a sink, a reservoir at lower temperature, and some working substance, which in the perfect Carnot engine cycle is an ideal gas that absorbs heat from the source, does mechanical work, and then gets rid of the excess heat into some kind of heat sink. So go through these couple of slides just to remind yourselves about the various components of the ideal Carnot cycle. But let's reduce it to the basics here. So at the top we have our heat source at some temperature T1. We're going to extract some heat, Q1, via a working substance. It might be, for example, burning fuel, producing steam to drive a generator, etc. So we're going to do some net work with that working substance. Any excess heat is then going to be dumped into a heat sink. Now in the perfect Carnot cycle, those two temperatures remain the same because they're assumed to be infinite sources and sinks. So, in the perfect Carnot cycle, we're assuming that the expansion and compression of the gases involved are going to be adiabatic, so there are no other losses, so we can simply write down the equations for the heat linked to the temperature as simply Q1 equals T1 times the change in entropy, ds, Q2 equals T2 ds for the sink, and of course the work done is simply Q1 minus Q2 in this figure. And if you take the ratio of those two equations up there, then Q1 to Q2 is simply the ratio of the heat source temperature to the heat sink temperature. Now in a perfect Carnot cycle, perfect heat pump engine if you like, we can define a Carnot efficiency as simply the ratio of the work done divided by the heat input, Q1, which is just the temperature difference between the heat source and the sink divided by the temperature of the heat source. And we can apply that to pretty much any system that's going to use some kind of working fluid to generate power. If we were to apply it to, for example, a power station, a big electric power station that burns some kind of fossil fuel, then the temperature of our furnace might be, say, 800 degrees centigrade, and T2, the heat sink, would be about 160 degrees C. So we could calculate a Carnot efficiency of about 60%. Now remember, that's for a perfect Carnot engine where we're assuming the ideal gas, if you like, is essentially following perfect adiabatic expansion, compression, and everything's isothermal where T1 and T2 don't change. Of course, that doesn't happen. And so we have to apply a slightly more realistic working cycle, which is called the Rankine cycle, where neither isothermal expansion and compression or adiabatic heating and cooling is achieved. And taking that into account, the efficiency of an ideal Rankine engine is around about 53%. But again, that's an upper limit. The actual efficiency of a good heat engine is about 89% of that Rankine cycle maximum. So again, the efficiency is reducing what we get out at the end of the day. So let's imagine the furnace in which our fuel is going to be burnt is 88% efficient. And they'll lose 12% up the chimney when we burn this fuel. Let's imagine that these very large electric generators are very efficient. They're about 99%. So our actual efficiency is 53% times 89% times 88% times 99%. The maximum is about 41%. And you can just about get 41% from these very large land-based power stations, which provide most of the main loads for electrical power generating networks. Usually, however, there's a mixture of smaller power stations which are required to kick in to provide additional demand, etc. So 30 to 40% is a good number to remember. Let's see, like previous person threw this example in, just to give you an idea about how we can actually make use of stored energy. And remember we talked about hydropower and barrages. Well, this is an example of a stored water system, sometimes called a pumped water storage system. And in fact, it's the only current form of energy storage, or it was until the wind farms and battery farms were installed in the UK, certainly. And many of you may or may not know that the largest pumped storage system of its kind is actually in Wales, in Dinorwig, near Snowdonia. It's actually built into the mountain of Snowdonia, behind some old slate quarries, Llanberis. So what they do is they pump water into a huge reservoir, the Marchlin Moor Reservoir, during a 6-hour period at night. The reservoir of this, the volume of that big reservoir is around about 7 million cubic meters, and it's at a height of 500 meters above sea level. So of course you can calculate the gravitational potential energy of all that stored water. It's around about 3.5 times 10 to the 13 joules. It's used to power generators with a typical output of about 1.8 gigawatts, so it's pretty impressive. But put that into context, the average power consumption in the UK varies diurnally from 25 gigawatts at night to a peak of about 50 gigawatts in the middle of the day. So how do we smooth out that consumption? Well, we're going to have to store 50 minus 25 divided by 2, 12.5 gigawatts for 12 hours. In other words, to smooth that out, we're going to need to store 5.4 times 10 to the 14 joules. How many Denoigs would you need to provide that? You'd need about 10, obviously, if we were to convert entirely to an electric economy with power generated remotely for end use. That's not kind of practical in the UK because there aren't very many places you can build such stations. Plus there are efficiency issues in terms of transporting that power generated to the point of use. Let's come down in scale now and look at slightly different efficiencies. Let's think about the house that you live in. One of the things about the Carnot cycle is you can actually run it in reverse to generate heat. And that's how space heating for homes and businesses works. So let's imagine we have a house and we want to actually heat it to some temperature, T sub R, so that's the temperature of our room. To do that we have to supply energy, let's say Q2. So if we run our Carnot cycle in reverse by putting work into our working fluid, we can extract heat energy from the external atmosphere, say, which is sitting at a temperature of T sub A. So Q1 is the energy that's essentially absorbed, and then we can generate heat that way. So in other words, Q2 is simply equal to Q1 plus W, the work we put in, and of course Q2 over TR equals Q1 over TA. And based on that, we can then produce what's called a coefficient of performance, or COP. And if you think about it, it's simply the inverse of the Carnot efficiency we defined in the previous slide. So let's imagine the outside air is 5 degrees centigrade in Manchester, and the temperature in this room is 20 degrees C. That would essentially give us a COP of just under 20. So if you think about it, what that means is that for every kilowatt hour you put in, you can get 20 kilowatt hours out. Sounds good. However, remember, the electricity we generate has to be taken into account in terms of its efficiency to put the power in to start with. Let's imagine it can be generated at 40%. That means we can just about retrieve all the original fuel energy with a COP of 2.5, 1 divided by 0.4, 40%. So the question is, can we do that? Remember, that's an ideal system. What does it look like in reality? Well, remember, in reality, we have to have some kind of radiators to collect heat and to emit heat. So there are lots of factors that actually reduce that COP we just calculated. So we might do work in with a radiator which is going to collect heat energy. And to do that, of course, the temperature of that radiator has to be maintained at a much lower temperature than the air temperature. To actually heat the room, we have to have another radiator, like those along there. And of course, those temperatures, the temperatures of those radiators has to be much higher than the actual average room temperature, say T2. So to transfer energy and heat efficiency, T2 is bigger than TR, and T1 is bigger, much less than TA. But you can do that. And for example, if T1 for our external collector is kept at minus 5 degrees C, T2, 45 degrees C, is what we're trying to maintain the temperature of our radiators at. Then, if TA is 5C and the temperature of the room we want to get up to 20 degrees C, that gives us a COP of 6.4, so a lot less than the COP of 20 that we initially estimated. That's why efficiencies are so important. So like the steam cycle, we can never realize a perfect Carnot cycle. the COP of the actual idealized cycle used, again we have to go to the Rankine cycle, is actually about 5.1, not 6.4. Real efficiency is never as good as those ideal limits because we have to allow for all these other efficiencies like heat losses in the circulation of the pumps and fans, etc. of our heat pump systems. And in fact, when you do all that and build something, the realistic value for the COP turns out to be about 3.0. That's just about sufficient to recover all the heat, waste heat lost in power generation. So it's got a slight advantage over standard heating arrangements where you can burn fuel on site to essentially heat water and pump it through radiators. That has an efficiency of around about 80%. So let's look at a house with a volume of 235 cubic meters and a COP, a good COP of 2.5. Let's imagine we have an all-electric house. So the first column shows the kilowatt hours needed for that house. So the heat pump, you'd have to supply 15,000 kilowatt hours. Other uses of electricity in the house, charging your iPad, etc. from the main socket, let's say 12,000 kilowatt hours. So the total might be of the order of 27,000 kilowatt hours. In terms of the energy delivered, we're looking at 37,500. We're looking at 12,000 for other uses. So the total is 49,500 in terms of the energy delivered. If we convert that to a fuel energy equivalent, assuming say 34% efficiency, we get up to 44,100 and 35,300. So our total is up to 79,400 now. Now remember, the efficiency of this system is the energy delivered, the second column, divided by the approximate fuel energy equivalent, 62% in this case. So that's the efficiency, or is it? If electrical power was costed at, well, let's choose a random number here, 5.5 pence per kilowatt hour, then the energy is going to be delivered at about 3.4 pence per kilowatt hour, more than 3 pence per kilowatt hour. Let's now change to a conventional boiler, same size of house, same values here. We don't need to supply any electrical power or negligible power to the actual boiler because we're going to burn fuel oil on site. And that will deliver 40,000 kilowatt hours. Let's say we've only require 6,000 kilowatt hours for other electrical power usage. So our energy equivalent at the end of the day is 67,600. The efficiency again we can calculate, 46,000 divided by 600, 68%. It's actually a bit more than our previous heat pump system. And again, let's assume electrical power is costed at 5p per kilowatt hour for this column. Let's assume heating oil, whose price may fluctuate quite a lot, is 20p per litre. Energy of combustion of heating oil is this number, 3 times 10 to the 7 joules per litre. If you work that out, the energy is delivered about 2.8p per kilowatt hour. Slightly less than 3p per kilowatt hour for the previous example. So they're about equivalent. So those are the sorts of efficiency issues you need to bear in mind when you're looking at different ways of producing electricity. So, what about the future? Well, by 2080, remember, we predicted that energy consumption would reach a steady state of 5 cube per year. We said that's very uncertain because it depends on population trends, etc., etc., etc. But it's dangerous to assume that that's going to be pessimistic. Assume that energy conservation measures, insulation, design, integrated transport, etc., etc., maybe we could reduce demand for our energy by, say, 40%. So we're down to 3 cube per year. Space heating, which we just discussed, is currently 16% of our electricity demand, believe it or not. But that's not going to be required by people living in the tropics, because it's going to get warm there anyway. However, air conditioning might be, so we need to think about that. But let's imagine we can reduce the demand by 0.3 Q, so we're now down to 2.7 Q per year. Of course, there is a penalty, as we said, for converting to all electric power. Let's say 50% penalty is the extreme value, so let's look for, say, 40%. Let's exempt space heating because of the use of heat pumps, which we just mentioned. So maybe that will increase the burden back up to 3.5 Q per year. And as we said, how does that compare to the resources we got available? Coal, we said we have to keep to maybe 0.2 Q per year, specialist uses only, emergencies. The alternative energy sources, excepting solar power, we might get half a Q per year out. But it could displace up to 2.5 times that value. So, after all those numbers floating around, what is the energy gap? There is an energy gap, obviously, and how do we fill it? Well, we have roughly 2.2 Q per year still to find. Where do we get it from? It's got to come from solar, it's got to come from nuclear. Fusion is not practical and won't be for quite some time, so it's got to be from fission, it's got to come from solar. Now, a lot of the assumptions we've made in this part of the course may seem a little bit arbitrary. They will change as technology improves, as more work is done. But remember, we've always tried to take the upper bounds in our estimates. So it's unlikely we're going to manage to actually get to our energy requirements or needs at the end of the century without such a deficit using current technology. So what do? Well, we have to make energy savings, but we would need to make about 50% over and above the 40% that we've already allowed for. That's a big challenge. Or we fill the deficit. Now, solar power may go a long way towards helping with that, but it's still quite unclear. So we have to make a decision on the future of nuclear power. There's no getting round it. Some people are arguing that carbon capture might be the answer. Google Carbon Engineering to see the first demonstration plant in Canada. But if you listen carefully to their advertising video, you'll see that the actual amount of carbon currently extracted back from the atmosphere is a drop in the ocean. It needs to be scaled up to very large amounts, but it could potentially contribute to, for example, transport fuel. As we said, there are other countries who saw this coming a long time ago, in the 1960s, 70s, not for quite the same reasons we're worried about now. For example, Sweden made the decision a long time ago to combine hydroelectric, wind power and fission. Their word for fission or nuclear power is kärnkraft. There's a short presentation on Blackboard if you want to look at it, which compares nuclear fuel, its advantages, with coal, oil and gas. It's one opinion. I'm not saying it's the correct one, but have a read of that because it's quite interesting. So, what we can say is we're going to have a very interesting future in terms of the energy generation landscape over the next 50 years. To finish, I'd just like to repeat a question that was posed to some physics and engineering students by a certain Dr. G.K. O'Neill. Some of you may have heard of him. Eventually ended up working at NASA. So he asked his students, is the surface of a planet really the right place for an expanding technological civilization? So they had an entire semester to go away and do their research and come up with an answer. And in particular, he also asked them what might be the ways to actually mitigate that expansion. And based on their research, he came up with the answer no. And this is what he actually wrote. It's important to realize the enormous power of the in red there is what the students highlighted would be the solution, which they came up with, although I think they were slightly guided by Dr. O'Neill because he was an expert in this area, of the technique. And he said if we begin to use it soon enough, this technique, and if we employ it wisely, at least 5 of the most serious problems now facing the world can be solved without recourse to repression, bringing every human being up to a living standard, now enjoyed by only the most fortunate, protecting the biosphere from damage caused by transportation and industrial pollution, finding high quality living space for a world population that's doubling every 35 years, finding clean, practical energy sources, preventing overload of the Earth's heat balance. Now the thing about that statement was that it was written in 1974. So scientists have been thinking about this issue for a long time. So does anybody know what's behind the red box? Somebody's smiling, I think they do. What's the solution, other than the ones we've discussed for this course? Well, they came up with the solution as being space colonization. Of course, it was just after the Apollo program, and a lot of people here might laugh, and certainly the politicians of the day say this was just fantasy and completely ridiculous, etc., etc. But they went to enormous efforts to actually calculate and design what a space habitat would actually look like in terms of their area, where they should be placed in orbit, how that orbit could be maintained in terms of placing 2 essentially joined cylindrical space habitats, providing sufficient space and solar power to essentially maintain life within that cylinder, or as Dr. O'Neill called it, Space Habitat Island 3. So I guess the question is, should this be your future? There are lots of people who say this is simply fantasy, but remember the original statement that was made in 1974. Pretty much a lot of what was said then is now becoming a pretty big problem today in terms of preventing overload of Earth's heat balance, population, pollution, etc., etc. I just thought I'd leave you with that interesting thought, and I now just want to spend the last 5 minutes giving you some advice for the examinations, or the examination. Okay, so hints for your exam paper. Now we've covered an awful lot of material in this course. There's no way that if I were to set an exam question that you'd have any idea as to exactly what to revise if I didn't tell you, give you some hints. This is on Blackboard, so I'll leave you to read this at your own leisure. But remember, you've got 4 questions, you can choose 2. Each question that you do is worth 25 marks, so you have 50 marks in total. You've got 45 minutes per question, but do spend a few minutes reading the questions carefully. Normally, there is 1 essay stroke structured type question with 3 numerical and extrapolation type questions where you'll be asked to estimate the answer to a question based on common sense input of values, whether it be kilowatt hours, whether it be population or whatever. Now for essay type questions, remember, try and use bullet points to provide a coherent, structured list, which includes, if possible, the primary most relevant facts, carefully selected or remembered from the best authoritative primary literature and statements, not something you saw on the news, mainly the IPCC, obviously. And you should also, rather than just dumping a list onto the piece of paper, just to show that you can remember lots of random facts, you should try and produce a narrative with reference to the most important aspect of the question being asked. And remember to give appropriate weighting to each of those parts in each of the bullet points. And finally, you should have a conclusion which should provide some balanced, salient evaluation and discussion that actually links back to the original question. So you have to again support that with some authoritative statements. For the extrapolation type questions, which we'll discuss in lectures, the tutorial lectures, remember bullet point key facts all the time, and also bullet point any principles at each step of your argument. You get marks for doing this even if you make a mistake in the calculation, remember. Always apply common sense to your calculations. If you come up with an answer that's plainly ridiculous, like the average kilowatt hours the average energy used per person per day is 1 million gigawatts or something, you know something's gone wrong in your calculation. If you can't find the error, say this doesn't make sense because I remember it should be in this range. At least it will show that you have some common sense. And who knows, you might get an extra half mark for saying that. Check the number of marks assigned to each part of the question. Put sufficient weight and time into answering those that carry the most marks. Don't spend a whole page and a half on a part of a question that's only going to give you 3 or 5 marks. So revision hints, which is what you've all been waiting for, and I'm sure you're all going to write them down. Except those who aren't taking the exams. Okay, as I said, we can't cover everything, so I have to give you some hints. These are the areas that you need to revise and focus on. So, problems associated with cloud optical depth, cloud droplet extinction, and cloud effective radius in simple stratocumulus clouds. So you should be familiar with the equations associated with all of those concepts. You should be familiar with the Earth's energy balance and also the equations associated with scattering from aerosol. So remember that aerosol model we looked at, and the equations. Single particle scattering albedo, etc., etc., etc. So make sure you're familiar with that part of the course. You should also, and this is really to test your background reading, be familiar with past and present climate change and evidence and impacts, particularly the evidence for human-induced climate change. I know it's a broad subject, but again, you need to be familiar with the background for that. And also, this year, please familiarise yourself with fossil fuel lifetime, reserves, and resources. I won't say any more than that. Now remember, in 1 or 2 of these equations, at least one question, you may be asked to prove or derive an equation. It's very obvious where those proofs might come in based on those hints. So, any questions? You're all going to pass with the average from last year of 68%, are you? Okay, good. In terms of past exam questions, again, you can find them on the library website. If for some reason you can't get hold of them, there are a list of them on the web page for this course under revision and tutorial material, including past exam papers. And again, the tutorial lectures, which we'll give when you get back from the holidays, 2 lectures, or tutorial lectures, they're also on there. In fact, there are 3 sets of lecture slides, but we'll only be doing 2 of them. And they actually show model solutions for some past examination questions. Obviously, they're not going to be the ones that are going to be in your examination, but they'll give you an idea as to the sort of expectations that are going to be expected from you. So I think that's it. I'll just leave that up. Any questions? You're all very quiet. Okay, has everybody signed in? Pass this down. You don't have to attend the tutorial lectures, they're not formal lectures. So if you can't make it, make sure you read the material on Blackboard. If you want to come and visit me and ask specific questions about those tutorial questions, you can arrange and come and see me on a one-to-one basis, or 2 or 3 of you at a time. So only in that first week, please. And best of luck in your examinations. For example, you might say in the text, ABC report date, and that's it. That's really the only one you would reference, unless there's a report or you can go about in this. That's the general piece of the lecture material. But anything in the lecture material you can use, but I'm not expecting a detailed list of references. When I say authoritative references, you can simply say IPC report says, and then list all the facts.
So there's no in-text situation.
No context. Well, you have to put your facts down. Rather than just putting a list, I like to see a narrative, a story. Like, these facts explain this, 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 and this. These facts explain this, 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 and this. This means that. Produce a story based on the original question. So read the question very carefully and make sure when you get to the end of your answer, ask yourself, have I actually answered the question? Rather than just put a whole list of facts down. You'll get fact marks for those facts, obviously. You get more marks if you actually answer the original question in a authoritative and what's called a reflective manner. So if you want to say something like, we need to, well, X% of the world's energy is by nuclear, Y% is by whatever, etc., etc. That means that we're going to have to look at replacing X% with, and then come up with a list of the alternatives. And you can use percentages, you can use cubes, I don't mind. There are some examples online. Don't expect that the essay type question is going to be easier than the numerical questions, because people might simply say, I don't like the essay, and they'll do the numerical question because it's easy to drive a proof. Environmental science students might say, I like the book work and I like to do the essay type. It's not really an essay, it's a structured question. It might actually have two parts to it, but usually it's just one part.
Will there be the same question with the past exam?
I can't tell you that.
Yeah.
Most of the questions will be variations of past exam questions, similar to.
Yeah.
There might be a few details changed, but obviously the course structure doesn't change, so
Yes, yeah.
Thank you.
okay.
Is it the same classroom for the next
The
tutorial?
tutorials, yes, it's the same.
Yeah.
If there's a change, I'll let people know.
Thank you.